All right, there. This is 2011, free response number 2. Unfortunately, I do not have the actual background like I did in the previous ones, and I'm not too sure how many more I'll be able to do, so I'm just going to keep trying. I'm going to try and finish this off and maybe do a few more years. So, starting from part A, it has you should have the question up and have completed it already. So, for part A, they want us to do an FBD of the object as it goes down the ramp at this exact point. Now there are, and it says not components, so that's probably the biggest thing, not components. I know usually whenever we deal with something that's like on an incline or on a ramp, I tend to tell you to always break up the forces into components, but in a problem like this, like always, do not include the components. There are only two forces that act on this object. There is the normal force, which acts perpendicular to the surface, and gravity, which acts completely down. And as you probably guessed, you got 1 point for basically doing the two forces individually and not including any additional stuff and having the arrows drawn properly. That was basically the full 2 points for that. Moving on to part B, it says in terms of theta and the magnitudes of the forces as drawn before. And this is equal to mg. They want us to determine the centripetal force at C. Now, your gut instinct will pretty much to say that it's Fn equals the centripetal force, but that's not the case. So we can't just say Fn equals mv squared over r. Okay, I'm glad my eraser doesn't work. So that's not what it is. And what we have to do is we have to realize that this gravity actually includes, or I should say, is part of the centripetal force. So I have to figure out the component of the force that is perpendicular to the surface to allow it for, that is also part of that. Because remember, the centripetal force isn't just a single force, it's the net force in that direction. So it's going to be in the plane of Fn, which includes a part of Fg. Now, the thing that you have to be careful about is what is that angle. They tell us that this angle is theta, which means that this angle's theta, so it should be Fn minus Fg sine of theta equals Fc. Now, as far as why it's, and that's pretty much all you have to do. Now, if you're trying to figure out why it's sine of theta, you have to kind of play around with the what's it called? With the geometry and try and figure out and make sure that the angles kind of work out. So because of the fact that the angle that they give us isn't technically the same angle that we're usually dealing with, it kind of says that this theta isn't necessarily the same theta over here. So that's not the actual theta. So you have to kind of play around with the geometry to figure out what this component is. Alright. And this was just a single point. Pretty straightforward. Alright, on to part C. Derive an expression for the speed of the compartment as it reaches point D. Alright, so easiest thing, since they want to just know what the speed of the object is at the bottom of the ramp, the easiest thing is just say potential equals kinetic. So we have mg h equals 1/2 mv squared, where this is vd. Masses drop out because that remains constant. Vd equals square root 2gh. You have to be a little bit careful with what r is. R is going to be the total height that it falls. It falls that vertical part of 3/4 r, and it also falls an additional r for the curved part. So you end up getting, that's 4/4, so that's 7/4, 14/4 gr, 7/2 gr. And yeah, so you ended up getting 2 points for this, 1 point for the answer, and 1 point for basically realizing conservation of energy. Pretty, again, very straightforward. D. So there is a force that acts between D and E, bringing the object to rest at E, and they want to know if it's brought to friction, what is the coefficient of friction? Alright, the first thing that pops into mind is, again, energy. We kind of did energy before, well now let's do energy again. This time though, the work done by friction is going to equal the kinetic energy it had at D. Force of friction, if you remember, is F of D. And that's just mu mgd equals 1/2 mvd squared mm. We just found out before that the speed of the object is going to be rad 7/2 gr squared, which is basically 7/2 r over d. Now I've been waiting to plug in what d is. Well, d, the distance from d to e, is 3r. So boom, boom. 7/2 divided by 3, so mu should equal 7/6. Now, wait. Oh, wait a minute. I forgot my half. Half, 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 half. Mu equals 7/12. Always want to double check your work. Yeah, I forgot the half there for a second. Now the good thing, the way you can double check to make sure this makes sense is make sure that this has no units. Remember, mu is unitless, so there should be no r, no g, no m in there. It should just be 7/12. Just some number. Alright, so this was 3 points. 1 point for using the v from before and substituting in for d, 3r for d. You got a point for coming up with the equation for friction, and 1 point for basically realizing that the work was related to the kinetic energy. Realistically, you should get into the habit of writing it like this. I know I've been kind of lackadaisy with it, but you really should remember it's this. The work is equal to the change in kinetic energy. And in this case, it's 0 minus 1/2 mv squared. Just something to keep in mind. Alright. And then part E. Part E says, okay. So this is the type of problem, like I said, is something that comes up a lot, and you really should have this in the back of your mind, written in the in your calculator. Now, the good thing about a problem like this is, even though it is tough, even for the people in the calculus class, it's a tough integration. You can get more than half of the points just by knowing how to set up the problem and then what the answer is. So you should know, for a problem like this, how to set up, which will usually net you 2 to 3 points, and then the final answer. And I'll tell you what the final answer is going to end up being. And like I'll show you a way to determine what the final answer is just by, without having to do any real math. Alright, so starting off it says, determine, we have a braking force that acts on this object, and they want us to solve, write but do not solve the differential equation for the speed. Alright, so we have an object that's being affected by some frictional force, some drag force that's speed dependent. So pretty much anytime you see something like this, a force that is speed dependent, that should trigger in your mind that you have to do this setup. Alright, so we know that F net equals ma. Pretty much if you're told to do a differential equation to find velocity, you want to do F net equals ma. And then we have negative kv equals ma. You want to make sure that you have that negative. It is important. Again, sometimes I could be lackadaisy with my signs, but in a case like this, it is extremely important to make sure you have your sign. Alright, and then, negative kv equals m dv dt. That's pretty much where you should end it, but I tend to like to kind of end it here. This is just you can end it here. I tend to like to end it here, and one thing that you may notice that I like to do is I actually like to keep my v away from everything, because that's my variable. I like to put all my constants together and then leave the variable all the way at the end by itself, mostly for kind of this reason. Alright, so this was 2 points. 1 point for basically using F net equals ma and plugging in that, and then 1 point for realizing that acceleration is just the time derivative of velocity. Alright, simple. Now for the second part, the double I. So now they want us to solve it, and like I said, this is where it gets a little bit tricky. So we left off here, negative km v. Alright, so this is what I mean by being able to set up the problem. Your first step when trying to solve a problem is to get like terms to one side. So that means you want to get the v with the dv, and then you want to put everything else on the other side with t. Alright, so dv. And remember, the only way you can bring v over is through dividing or multiplying. You cannot add v to the other side. It has to be divided over or multiplied over. Alright, so then we have dv km dt, and right there is your first point. So without doing any real calculus, right there, you got 1 point for setting up the problem. Boom. Alright, now like I said, this is where it gets a little bit trickier, because now you actually have to integrate it. So we have dv v equals negative km dt. Integrate both sides. Remember, t always goes from 0 to t. Here, velocity goes from initial to final. When I look back at my problem, the object does have an initial velocity of vd, and its final velocity is just some v, because remember, v is the variable. Alright, and then we do this. The integral, if you remember, of this is just really the same thing as writing negative km integral 0 to t of dt, which is just negative km t from t to 0, which is just negative k over mt. Alright, so the t is always the easiest, and it always ends up being this. This part is a little bit trickier. Luckily for a problem like this, it's not actually that hard. This is something that you just kind of have to remember. It's actually in the reference table on the last page. The integral of something like this, dv over v, will end up being ln, absolute value technically, of v from vd to v, which means that's just ln of v minus ln of vd, and you can combine those into a single ln by doing v over vd. And all this is equal to that negative k over mt. Now, anytime you deal with drag, anytime, whether it looks like this or it looks like an object that's accelerating to terminal speed, you always will end up getting something that looks like this, and you will always have to get rid of the ln by raising both sides to e. It's a common thing. So you raise this to the e and that to the e. So this just becomes e to the negative kmt. But, that. But this part, what this does is it crosses out the e and the ln, leaving us with just v over vd, which equals e to the negative k over mt. Alright, I want to get this v by itself, so I multiply the vd over, and I'm coming up with this equation. And there's your second point. So all this work for pretty much 2 points. Now, like I said, you don't even really have to do all these steps, because of the fact that if you know how to set it up and you know what the final answer is going to be, then you don't really have to do anything. Now you may be wondering, well, how do you know that this is going to be your final answer? Alright, and I'll tell you. So, pretty much, anytime you have a drag force problem, the velocity, so this is anytime with drag, it's always going to be, the force is going to be equal to some constant, let's call it A, times V. The constant changes. Sometimes it's B, sometimes it's K. You kind of have to go with the flow with it. But if you want to know what the equation was for the speed is always going to be some sort of the maximum speed times e to the negative amt. And let me put a little, let me say this is B. minus. Alright. Let me just say this. Alright. And it's going to end up having something e to the negative a over mt. Alright, now the something really depends on what the problem is. So let's say we had an object like this, brought to rest by the drag force. It's going to end up being the initial speed times e to the negative am over t. Now when you do this, you'll notice that it starts from some initial value, like if you graphed it, velocity versus time, you graph it, it should start at some initial value going down to 0, which is something we would expect for a for an object being brought to rest by a drag force. For an object that is I guess coming to terminal speed, so in this case, in the first case, the drag force is bringing it to rest. In this case, the drag force is actually just making it so that it doesn't go too fast. It's limiting the speed. So maybe saying that, limiting speed. It's going to end up looking like the terminal speed. Misspelled that. Times 1 minus e to the negative amt. So notice how this equation still has the same e to the negative amt. That's still there. And it still has some initial velocity in both cases. Again, and it's always the maximum value that it will reach. Here, it's the initial velocity that the object initially starts with before it decelerates. Again, it's maximum speed. Here, this is the maximum speed that it's going to reach when it's moving at a steady speed. The only difference is whether you have this 1 minus part before it. And the way this one works, if you graph it, is you'd end up getting a graph that looks something like this. Again, something that you would expect with terminal speed. It's speeding up and then leveling off. Now, the one way that you can figure out what the terminal speed is by just doing f net equals 0, fg equals whatever the drag force is, and then solve for v. Alright, so these are your two different scenarios. I can't think of another scenario that they would have, but these are the only two scenarios that I could think of that deal with the drag force that you might be expected to have to integrate. But again, you get most, if not all, the points without having to do any type of integral, just by knowing how to set it up, by splitting the variables, and by realizing how to figure out what the equation is going to look like. Again, two scenarios: brought to rest by a drag force or coming to a terminal speed. Those are your two scenarios. And as I said, this A term is going to be basically this, like, just some term that they give you. Sometimes it's B. In this problem, it was K. Alright, continuing on, they said they want to know the graph of the acceleration versus time. Alright, so, well, first off, I know that, so normally, this is going to be my normally line. The acceleration should be constant. Right? In a case like this, though, using F net equals ma, negative kv equals ma, alright. Now I dropped the negative because remember negative's constant is just a direction, and this is specifically asking for the magnitude of the acceleration. So what this means is that it's going to have some maximum value of this. And this is going to be true whether we're talking about it normally or whatever. Now, the problem is that it's not this value, even though its maximum is when v equals vd. That's not always the case. V is changing. It's constantly decreasing as the object goes farther away. So as it moves along, it decelerates, so the speed decreases, which means the acceleration has to decrease. And I said before that the velocity versus time is going to look something like this, so the acceleration graph actually looks exactly like that as well. So that's your actual graph. Alright? So you got 3 points for this problem. 1 point for realizing that this graph starts at some initial value. And again, you got 1 point for even labeling what the correct value is. 1 point for knowing that it starts at some, not starting from infinity on that y-axis, but at some fixed value. And then 1 point for realizing that it was curved upwards like this, reaching 0. So what they mean is, like, if you drew like this, that would be a no-go. It would have to be something that making it so that it actually never goes to 0. Because if you think about it, if the acceleration is based off the velocity, and the velocity changes because of the acceleration, it's going to be a constant circular loop that will never let it go back down to 0. Because as the speed gets smaller and smaller, the acceleration becomes smaller and smaller, which means that the speed changes less and less, which means the acceleration, and it just comes, it almost ends up being an infinite loop where the object will never actually go to 0. Though for the most part, in all intents and purposes, it will come to 0 at some point. Alright, and that was basically it. Like I said, the biggest thing that you have to remember to do for this problem is to write down in your calculator how to set up a drag differential, so how to set up the equation for a drag force, and then to be able to know what the answer is going to be for those two cases. If you have any questions, let me know, and continue practicing these problems.